Hi everyone, my name is Kathryn Aldridge and I'm a master's student in the Crop Imaging and Agronomy Lab at the University of Saskatchewan, and today I'll be talking to you about the classification of Trifludimoxazin, Saflufenacil, and Pyroxasulfone's herbicide interaction for the control of false cleavers and wild oat. So today I'll be talking about an introduction for herbicide interactions and Colby's equation, as well as my experimental objectives and materials and methods, then focusing on my results for both weed species and the conclusions I came to. The development of herbicide-resistant weeds threatens Western Canadian and global crop production. As you can see, there's a large number of herbicide-resistant species for each crop type, which highlights the need for effective alternative mechanisms of herbicide action. So take mixing two or more effective modes of action is a way to delay resistance. Herbicide mixtures are an ideal weed control option for producers as they can increase the spectrum of weeds being controlled. Herbicide mixtures can react through a variety of ways, including synergistic, antagonistic, or additive, and they all influence the level of weed control and crop tolerance experienced. Antagonistic herbicide interactions have reduced efficacy and weed control. An example of this is Saflufenacil and clomazone. Synergistic interactions occur when the combined action of the two herbicides is greater than the predicted model. An example of this is Saflufenacil and metribuzin. And additive herbicide interactions efficacy is the sum of the activity of the combined herbicides. An example of this is Pyroxasulfone and sulfentrazone in sunflower. So Colby's equation can be used to determine the type of herbicide interaction in your herbicide mixture. So there's the formula. E is the expected biomass as a percent of the untreated check when both herbicides are applied. X and Y are the effects of the herbicides applied alone at rate 1. So X in this experiment is group 14 at rate 1 and Y is group 15 at rate 1. So then you compare the actual versus expected weed control to determine the type of interaction taking place. So if the actual weed control is greater than expected, you have a synergistic interaction. If it's less than expected, you have antagonistic. And if it's equal to what was expected, you have additive. My experimental objectives: to examine the herbicide interaction occurring between Trifludimoxazin and Saflufenacil, my group 14s, and Pyroxasulfone, group 15, in false cleavers and wild oat, and determine the type of herbicide interaction present, whether it was additive, synergistic, antagonistic, or no effect. And it was hypothesized that combining these three herbicides would result in an additive interaction where the expected plant response is equal to that observed in false cleavers and wild oat. So this was a dose response randomized complete block design with 4 replicates. Each experiment was repeated 2 times for each weed species, and the herbicide treatments were comprised of 2 factors, including herbicide group and rate. So for the potting mix, it was a 2-to-3 ratio of sunshine mix number 4 to clay sand and organic soil, and a flat fan nozzle with a 0.15 gallons per minute flow rate at 40 psi was used to apply the herbicide treatments. So the pots were watered to field capacity, and the herbicide was allowed to equilibrate within the soil for 3 days prior to seeding. The weed seeds were seeded 1/2 inch deep and then thinned to the appropriate number upon emergence. So false cleavers ended up having 6 plants per plot and wild oat had 4. And the plants were grown with an 18 to 6 photo hour period at 25 degrees Celsius during the day and 18 degrees Celsius at night. And aerial view images were taken to monitor the herbicide injury progression throughout the experiment. False cleavers had 10 rates in the experiment, ranging from 132 to 16 times the herbicide rate. Wild oat had 9 rates, ranging from 1/8 to 32 times the herbicide rate. A bit more about each group individually. Group 15 is Pyroxasulfone, where the 1x rate has 60 grams active. Group 14 is BAS 851, which is a 2-to-1 premix of Trifludimoxazin and Saflufenacil, where the 1x rate has 18 grams active. And then the combination of group 14 and 15 is the combination of the 2 actives, where the 1x rate has 78 grams active, and also untreated checks were included. So there were 3 evaluations performed throughout this experiment at the 7, 14, and 21 day after emergence timings, and also at the 21 day after emergence timings, the above ground plant biomass was taken. So each weed was cut at the soil surface and weighed to get the fresh weight, and then they were put into the dryer for 48 hours, after which I took them out and weighed them to get the dry weight. Weed biomass data was analyzed using log logistic models in the DRC package in R, and all model parameters were compared using the comparm function in the DRC package. Model selection for both false cleavers and wild oat were based on a non-significant lack of fit test, examination of model fit to the data, and of the model residuals, and all model residuals did not meet the assumptions of the ANOVA, and therefore all of my analysis was transformed using the optimal Box-Cox transformation. So for this analysis, means were declared significantly different at p is less than 0.05 when comparing the model parameters. So on the slide here is a 3-parameter log logistic equation, and this is what all of my models ended up being. Y represents the biomass, D is the upper asymptote, E is the ED50, which is the effective dose to reduce biomass by 50%, and B is the slope around the ED50. So false cleavers, combining the group 15 and 14 herbicides resulted in the upper asymptote value to decrease, which indicates that less false cleaver biomass was present. And then comparing all model parameters, the ED50 was found to be significantly different between group 14 and the combined, with a p-value of 0.004. And all other model parameters were not significantly different between the herbicide groups. The combined group had the lowest ED50 estimate, indicating that less active ingredient was needed to reduce false cleaver biomass by 50%. The ED50 of group 14 equaled a 22.3 gram rate, while group 15 equaled a 47.5 gram rate. The combined equaled a 44.4 gram rate, with 10.3 grams being group 14 and 34.2 grams being group 15. So looking at the figure here, increasing herbicide rate resulted in a reduction in false cleaver biomass, and all of the herbicide groups followed a similar trend in their regression line when plotted for biomass reduction, being relatively parallel to one another. Looking at false cleavers visually, on the left is the combined. Growth really started to reduce at the quarter rate with no growth present at the 1x rate. In the middle, group 14 individually, growth really started to reduce at the 1x rate with no growth present at the 8x rate. And on the right, group 15 individually, growth was greatly reduced at the quarter rate with no growth present at the 2x rate. So Colby's analysis was done to compare the expected plant response to the actual plant response, and all model parameters were compared. Again, this was done with a 3-parameter log logistic model using the optimal Box-Cox transformation, and no model parameters were found to be significantly different from one another. Therefore, group 14 and 15 herbicides have an additive relationship. And looking at the graph, the actual plant response and expected plant response points are very close together, particularly at the higher rates. Therefore, the level of weed control obtained from the combination of Trifludimoxazin, Saflufenacil, and Pyroxasulfone was equal to the predicted level of control for the combination of herbicides based on each group's individual efficacy. Moving into wild oat now, again, a 3-parameter log logistic model was selected using the optimal Box-Cox transformation. And comparing the model parameters, no upper limits were found to be significantly different between the herbicide groups. However, group 14 was significantly different from 15 or the combined for its slope and the ED50, as it required much more active ingredient to reduce biomass by 50%. Group 15 and the combined were not significantly different from one another for either parameter. The ED50 of group 14 equaled a 72.7 gram rate, while group 15 equaled a 16.2 gram rate, and the combined equaled a 31.2 gram rate, with 7.2 grams being group 14 and 24 grams being group 15. Looking at the figure, increasing herbicide rate decreased wild oat biomass, shifting the curves downward. In the plot, the combined and group 15 follow the same trend and are similar to one another. However, group 14 does not begin to decline until the 1x herbicide rate. Looking at them visually now, group 14 alone on the left, growth really starts to reduce more visually around the 2x rate until there's no growth present at the 16x rate. The combined group in the middle, growth greatly starts to reduce at the quarter rate until there's no growth present at the 8x rate. And on the right, group 15 individually, growth is starting to reduce at the half rate until there's no growth present at the 16x rate. Colby's analysis was again conducted, and this was done using a 3-parameter log logistic model with the optimal Box-Cox transformation, and no model parameters were found to be significantly different between them. Therefore, group 14 and 15 herbicides have an additive relationship. And looking at the figure, the actual versus expected plant responses are very close together along the regression line. So in conclusion here, for false cleavers, the mixture of group 14 and 15 herbicides improved control compared to the individual herbicide groups. For wild oat, the group 14 and 15 mixture performs similarly to group 15, with the addition of group 14 adding small improvements. Both weed species displayed additive herbicide interactions, and tank mixtures improved herbicide resistance weed management for both weed species. Thank you to my supervisors, Eric Johnson and Steve Shirtliff, for their help with this project, as well as the staff at the Phytotron facility and the Kernan Crop Research Farm for their help with this project. And thank you to BASF Canada for their funding. Thank you. Do you have any questions?